This question asks, what is the best synthetic sequence to accomplish the following transformation? So if we take a look at our sequence, we start with benzene and we end up with a di-substituted benzene. Based on the substituents, we have a nitro group. So we know nitration is involved at some point. And we also have an alkyl group. So we're either going to need alkylation or acylation in order to add that substituent. So the key here is what order do we use? What reactions do we use? So let's go ahead and take a look at our options. In our first case, we have an alkyl halide reacting with aluminum trichloride. So this is an alkylation reaction. But the key thing to recognize about this very first instance is that we have a primary alkyl halide. And we learned that primary alkyl halides can rearrange. So if we were to think about the product that we would form in this reaction, that first one would give us a carbocation that looks like, that looks like this, which we know would rearrange into a tertiary carbocation. So the final product that we would make would be a tert-butyl benzene instead of the desired alkyl chain, which is a sec-butyl. Okay, so we can cross off number one from consideration because, or A, sorry, from consideration because the alkylation will rearrange and we won't get the desired product. Let's take a look at reaction B. Reaction B has nitration occurring first. So if we nitrated our benzene ring and then we tried to alkylate, we would add at a meta substituent or a meta position. And we already know that that's not going to be ideal because up here at the top, we have para substitution. So we need to probably not do nitration first. Another key thing to keep in mind is that Friedel-Crafts alkylation and acylation reactions don't really work well if the ring is already deactivated. So that's another reason why nitration first doesn't work well. So let's cross off this option as well. If we look at C, we have the same problem. We have nitration first, followed by an acylation this time. The nitration, again, is still going to direct meta, so we don't want that one either. So let's move on to D. If we take a look at D, we have acylation, and acylation will work and add the R group that we would like. We would end up with this molecule. So the carbon skeleton is correct. We do need a second step here. The zinc Hg, HCl and heat is the Clemmensen reduction, and that's going to reduce our carbonyl. So that allows us to kind of get around the rearrangement issue of the alkylation not working. So here we use acylation followed by reduction, and that allows us to add kind of like a primary alkyl group to the benzene ring. Last step is nitration, and this group here is an OP director because it's an alkyl chain. So this one will correctly make the product that we would like. We would get NO2 para. And so D definitely works. All right, so I'm going to give that a nice check mark. Let's double check E2 just to cover all of our bases and make sure that E will not work. So if we take a look at E does the acylation. We have our ketone, and then in E, nitration occurs second. And that's not ideal because we still have an electron withdrawing group right here. And so it would also add to a meta position. So we can now cross off E because it wouldn't give us the correct substitution pattern. So our answer to this question is reaction D will allow us to correctly make the desired product.